Hello, and welcome to this second video of the series on linear algebra for quantum mechanics. In this video, we will extend upon the concept of complex numbers, which we have seen in the previous video. What are complex numbers? They are a combination of real coefficients with imaginary component, as we have seen before. For example, z equal to a plus bi, where a and b belongs to the real numbers and I is the imaginary component. We will now extend upon the properties of complex number, which is very important to understand some deeper context in quantum mechanics. We shall start with the complex conjugate. It is represented in a, for example, x and y format where x represents the real number axis and the y, for example, represents the imaginary number axis. Complex conjugate means that then complex number has a mirror image over the real axis, which just falls on the other side of the axis. So for example, as you can see in the example here, the complex number 2 plus 2i has a mirror image below the real axis, which is represented by 2 minus 2i, which is to say that a complex conjugate is symmetric over real axis to a complex number. A complex number is not just only denoted by point in the plane, but it also has a measurable magnitude, and that is represented by calculating the magnitude of the coefficients which are from the real number category. So in case of a complex number in the format z is equal to a plus bi, the magnitude will be represented as under root of a square plus b square. In this slide, there are few examples that has been shown as to how to represent the magnitude and how it is calculated. So for example, if you see for 2 plus 2i, the magnitude calculation, and also for another reference complex number 2 minus 4i, the magnitude calculation. An important property of complex number is phases, which is basically how trigonometry gets combined with complex numbers in doing some complex representation. And it is represented by the angle theta from the real axis, which is basically arc tangent for the coefficient of b by a. It has to be noted that the theta lies in value between 0 and 2 pi. There is some example of how you can calculate the arc tangent of a complex number, which is basically the phase, which will help to decide between how far the complex number is aligned in terms of the real axis of the complex plane. Another very important property is the Euler's formula, which helps basically to decompose the real and imaginary part. It's represented in form of a circle such that the formula e raised to the power I phi will hold and equals to cos phi plus I sin phi, which represents the real and the imaginary component of a complex number. In terms of calculation, if you put on the value of phi to to a irrational number, say pi by 4, you will get to see the value of this unit circle and how it's represented on that particular point. It's important to note that an unit circle is represented in a way such that all points on the circle, on the circumference of the circle, has a magnitude of 1, which means the square of coefficient a plus b should hold to a value of 1. This is a very important concept to understand further when we will talk about the qubits and the representation of qubits, so please do pay great attention. I'll stop here and I'll hope to see you in the next video. Thank you very much.